So it is my great pleasure to introduce Neha Rungta. Neha currently serves as a Director of Applied Science at AWS. Neha is a world-renowned expert in applying automated reasoning to real-world systems at unprecedented scale. At AWS, she has led the design and launch of foundational security services, including Amazon S3 Block Public Access, YAM Access Analyzer, and most recently, the CEDAR Policy Language and Amazon Verified Permissions, powering scalable, provable access control across the cloud. Her groundbreaking work has transformed the role of formal methods in industry, enabling trillions of verified authorizations daily. Prior to AWS, Neha was a research scientist at NASA Ames Research Center, where she worked on verifying the correctness of unmanned space systems and conflict detection algorithms. She is a builder, a scientist, and a leader pushing the boundaries of what trustworthy systems can achieve. Neha Rungta is a true visionary technology leader and a pioneer at the intersection of formal methods, cloud security, and applied science. So welcome.
Thank you. Thank you, Karina, for the very kind introduction. And it's fantastic to be here talking about the things that have been going on. So today I'm really going to focus on how we achieved some of the things that Karina mentioned. How did we get to correctness at the scale that AWS operates at? So before we begin, the question we want to ask is, does automated reasoning scale? And the answer is yes, it does. And today I'm going to show you how we've proven that it actually does scale at industry at the level AWS operates. And we have been applying formal methods and automated reasoning across Amazon's critical infrastructure. And we are not just talking about verifying simple algorithms or toy examples. We are talking about verifying actual boot code that is running on millions of servers across Amazon's data centers. We are talking about mathematically proving the correctness of TLS protocols. We are talking about looking at formal verification of key management systems. And these secure countless transactions every second. We extend it to rigorous proofs about the behavior of complex distributed systems. And I want to really emphasize that these aren't just theoretical exercises. They're practical application protecting real infrastructure at massive scale. And the fact that I can show you this published work demonstrates something crucial, that automated reasoning has moved beyond the theoretical and moved into the realm of solving real-world problems at enterprise scale. But I've used the word scale a few times. And I want to be precise about what I mean by scaling before we begin. And in my mind, there are two distinct dimensions of scale. One is scaling up, where we tackle increasingly complex problems that require deep proofs and very sophisticated reasoning. The other dimension is scaling out, where we apply automated reasoning horizontally across many similar but distinct problems. So when we are proving the correctness of large-scale systems, think about distributed databases, encryption algorithms, or operating system components. These actually need complex and integrated proofs. We are talking about handling concurrency, dealing with failure modes, proving properties about asynchronous routing. The proofs can get hairy, they can get deep, they can get complicated. And traditionally, this kind of work has been the domain of experts. We call them automated reasoning experts, and as a shorthand in AWS, we call them AR expert. It's just somebody who has knowledge in formal methods, programming languages, theorem proving, mathematical logic. And when we talk about scaling out, there's it means to many smaller problems. We are looking at things like individual cryptographic protocols, specific access control policies, security configuration, programs, infrastructure as code templates, network routing rules. These are all smaller but very distinct problems. And here, the key point is this verification needs to be done by domain experts, the people who actually build and maintain these systems. So you can have security engineers who understand the crypto protocols. You have DevOps engineers who understand the infrastructure that they're building, and network engineers who design the routing properties. And if we look across, we've had several examples of the use of it. We've had very successful examples in scaling up, as well as when we look at scaling out. We look at SL4, CompCert, Ironclad are great examples of scaling up, as well as we have Rust and Slam, Coverity, Infer as examples of scaling out. So today, I'm going to show you how we've successfully scaled out automated reasoning in Amazon. That is the focus of this talk. And it's going to be in three critical areas: security, identity and access management, and in governance. For each of these areas, I'm going to show you the specific problems that we needed to solve to scale out, how we got there. And the spoiler alert, it's a foundation we built for domain experts, and the scale that we are operating at, as well as the real-world impact this has had. I want to take a minute to say, why has it been so hard traditionally? And there is a counterintuitive point here. Scaling out is actually harder in some ways than scaling up. When you're scaling up, you're trying to verify one large system, one big system. You have a core group of people, your experts. They need to align on formal definitions. They agree on proof strategies. They agree on the tools. And they can work together to solve the complex problems. The key here is they have the same vocabulary of what does it need to do. They have the same language of formal methods. They're all trained in the same technologies. But when we're scaling out, we are dealing with lots and lots and lots of little systems. And you end up supporting hundreds of thousands of users, if not millions of users. Each of the user comes with their own mental model. Each comes with their own way of thinking of the problem, and each with their own definition of what does correct mean. And different people define it differently. A security engineer says, oh, my resource should not have public access, while a compliance officer may say, my resource should have no unintended access, while a governance person may say, my control should be correct. I'm going to start with what are the things we know that already don't work. We can say, how are we going to get hundreds and thousands of users writing formal specification? We know that doesn't work, because most wouldn't even know where to start. They'd each define things differently. The specifications would be inconsistent. And let's be honest, nobody needs to learn a new specification language. We can't have hundreds and thousands of users doing formal proofs either. That's not their job. They have systems to build and maintain. They need answers in minutes, not in days. And they don't even have time to debug failed proofs. What else? We can't expect all these users to keep the specification, the code, and the proof synchronized. These systems change continuously, and the requirements evolve. This is a full-time job. Even for automated reasoning experts, they struggle with this. And finally, and most importantly, we can't just say we'll teach automated reasoning or formal methods to everyone. We'll make them experts. That is just not realistic. It's not scalable. It's not their core competency. And frankly, that's not what they signed up for. So, okay, I've been a little bit of a negative Nelly. I've talked about all the things that we cannot do. So what are some things we can try? We thought, can we meet them halfway? We can provide them some tooling. We can provide them some specification, like have them write some specification. We handle the proof automation. But they would still need to learn our language. And that is still too hard. Okay? What's the other option? Can we meet them 3/4 of the way? Okay, we're providing some more intuitive interfaces, better usability. They can work with simplified rule sets, and we'll handle the transition to formal methods, but they still need to think in our terms. We can keep going. 7/8 of the way, we provide more domain-specific tooling, and they still express what they know in familiar terms, but we handle the formal machinery. The key is they would still need to learn new concepts. And remember, we are talking about hundreds and thousands of users. Can we meet them all the way? Now, this is an interesting question. And this is what the talk is about. How did we meet them all the way? How we managed to make automated reasoning invisible while making it ubiquitous? Could we let them work completely in their domain language? Could we let them express properties as they naturally think about it? Can we hide all the complexity of formal methods and just make them feel like they're doing their regular job? The insight was, how did we get there? And the answer is domain-driven foundations. This was the key insight that changed the game for us. Because you see, the domain experts haven't waited for formal methods to come along. They've already been solving really hard problems, and they've defined best practices, they've defined design patterns, they've designed review processes, validation checks, testing frameworks, standard operating procedures. They've done a lot of work to solve the problems in their domain. And our job isn't to teach them formal methods or to make them write specification. It would be too onerous to force them to learn theorem proving, because they would need to now replace their existing solutions, and we would be telling them, all the time that you've spent doing this work, you've been doing it wrong. And nobody likes to be told you've been doing it wrong across your entire career or entire workforce. That just doesn't work. So, okay, so what do we know that they already have? So we're like, they have deep domain knowledge. They know their domain the best. They already have well-defined vocabularies. They have established way of how they think about it, and they have proven practices. That has worked. It's not that without formal methods that their techniques don't work. And they actually even have notions of correctness which are clear to them. They just don't translate into logic like we would like. So with this, our goal is, okay, if we can get foundations in place, then we can build formal methods upward together, amplifying their expertise rather than replacing it. And I hope by the end of this talk that you're convinced that it is possible. I'm not going to say it's easy, but possible. The complexity and computability in computer science theory. And once we know that it is possible, we can start to apply it to more domains to make it more ubiquitous. So I said we're going to do these 3 categories: security, identity, and governance. But there is an underlying foundation to these all of why what I'm saying is even possible. And that is cloud computing. And you may say, like, what has cloud computing to do with this? It has got everything to do with why we were able to do this scalable automated reasoning across so many domains. So the insight here is, hopefully a lot of folks know what cloud computing is by now, but the key insight is it gives us critical capabilities such as infrastructure as code, where every resource is defined in code. Every configuration is explicit. Everything is programmable. Everything is trackable. There are APIs for everything. Every resource has a schema. Every permission is denied. Every state is queryable. You have centralized control planes that give you a single source of truth. You have consistent enforcement points. You have unified audit trails, and you have standardized interfaces. This means we can reason about the configurations before the deployment of a resource, verify the changes as they happen, and check permissions systematically. The cloud isn't just where we run the systems, it's how automated reasoning is possible at scale. Another way, as software engineers, to think about cloud computing is it's about programming with a new function whose return type is a computer. Now, we think of functions that return integers, booleans, files, sockets, but now you have a function that returns a computer. But what's very interesting is how would you program with this function? Now, if you're building an application that uses a database, when your utilization of the application gets high, your system could call this function, get a fresh computer, shard a part of your database onto the new computer, and scale up. Later, when utilization drops, there's this wonderful function f inverse that takes a computer and gets rid of it. With these two functions, your system enables the user's database to scale up and down automatically. And to make this even easier to use, the cloud computing provides you a combinator function G, which wraps f and f inverse. It gives you a database as a return value, and it uses f and f inverse internally to make the database scale up and down automatically. This is what's the AWS console. It's essentially a web page that lists hundreds of services available through AWS. Here's a few of them covering compute, developer tools, databases, storage, media. A service, Lambda, lets you run code without managing servers. When you call the function, it creates a server, runs your code, destroys the server. And it is F inverse composed with your code, composed with F. This is serverless computing. There are other functions that return reliable queuing, durable data store, fast key-value pairs. And this is incredibly powerful functions at this point. Now, you may wonder, who's allowed to call these functions? Should the people administrating these resources be allowed to call the function? Should the people programming be allowed to call the functions? Should graduate students, should interns who have come for an internship be allowed to call these functions? So we're going to find out what happens. Let's zoom in on S3, our durable data store, which is essentially made up of about 100 distinct APIs. And I'll give you a flavor of these APIs. The put object API lets you put data in an S3 bucket. That's what the container in S3 is called, a bucket. Get objects lets you get a data block out of the bucket. You can delete data. You can list what data you have in the bucket data objects. You can get metadata attributes about a particular data object, and so on and so forth. And to control access to all these APIs, users of the cloud write access control policies. And these policies can either grant access to particular APIs called actions, to particular users called principals on any particular resources, which are called resources. And you can essentially have multiple allow statements. There's also deny statements. So the deny statements will take away permissions that are given by allow statement. And if you have no statements, access is denied by default. It's an implicit deny. It's secure by default. So when you make a request, you either through the CLI or through the command line, through an SDK, through the console, when you make a request to access a resource, it's evaluated against a policy, and access is granted only if at least one allow statement matches and 0 deny statement matches. And it's easy when you look at these policies to translate them into logic, because like there is a structure to it. And I'm sure there's some of you who's already imagining, hey, for these kind of policies, what are the SMT formulas that can be created out of these? And this is the first thing we did. Of course, as logicians, as formal methods experts, we were like, let's create SMT formulas from these. And we built exactly that. We said, okay, if you want to know your policy is correct, encode your notion of correct into logic that is represented as a probe policy, then perform a comparison between the policy and the probe policy, and then you can either get an answer that the policy is either greater than or less than, or they're incomparable because there may be some overlap in the permissions, or maybe we draw a Venn diagram. As you can tell, we did not have this notion of domain-driven foundations when we started that work. We were struggling. We were doing what the classical problem is with formal methods. Hey, let's teach them how to convert their problem into logic. And it actually did work for some eager users, some people who were interested and had the aptitude, but that was a very small set. And for most, it didn't work. So we took a step back. Instead of saying, we're going to prove the correctness of your policies, we started listening to what the users actually wanted. And the number one thing that the users wanted was, did my bucket allow public access? Awesome. That's great. We have a property. But what does public mean to you? It turns out public is a very tricky notion to pin down. No individual person considers themselves the public. I'm not the public to me, but in the aggregate, we are all the public. So as you can see, the notion of public doesn't decompose very well. If a bucket is shared with the New York Times, does it make it public? For your bucket, the answer is yes, but if the bucket is owned by the New York Times, the answer is probably not. What's public to you might not be public to someone else. So, okay, but it's maybe too hard a problem. As we were wrapped up trying to solve the problem, we had almost forgotten to ask the questions, how do the security engineers solve this problem today without formal methods? And the answer was clear. They say, oh, we check to see if it has trusted access. It's like, okay, that's the key. There is a difference in the words we were using and the words that they were using. Trusted is a much easier notion to pin down. If I trust this whole room, I trust individually each one of you. Trust decomposes really well. If I trust each one of you, then I also trust this entire room. Trust happens to also compose really well. So instead of trying to pin down public, we pivoted to trying to pin down trusted. And this is how we formalized public access checking. We defined public in terms of trust. And once we focused on trust, the rest of the path was very clear. We ultimately checked to see if access is allowed that is not trusted, exactly what the users wanted us to verify. So let's take a closer look at the notion of trust. How did we define it? It's still a bit tricky to define. It's not as easy. We at least now have foundation and properties of composability and decomposability, but it's still tricky to define. So trust is composed of two components: what can be trusted, and examples are users' accounts, networks. What's not trusted is username. You can just go create a different username, or just saying, oh, this request needs to be encrypted on HTTPS. That by itself is not sufficient because an untrusted party could send an encrypted request to get access to your data. So the second component of trust is what are the specific values? Specific users, specific accounts, specific networks. And where do we get these specific values from? The trick, the cleverness that we used was to extract them from the user's policies itself. We didn't want to make the users define it another way. The whole notion of a policy is the fact that they are defining what they want access to. So what can be trusted? A principle, we said, is trustable, and it has a very specific value. So we can say, this is trusted. Here's another example. There is no trust here because the username cannot be trusted. Anybody can go and, in an account, create a username and create a request from that. I'll give another example of where there is no trust. A source account can be trusted, but trusting all accounts that start with 1, 2, 3 is nonsense because source accounts are not given out in some order. You are essentially not bounding it in any meaningful way, the specific values of a source account. So we took that, we encoded that, and then launched it into a public-facing feature called S3 Block Public Access. Users can turn it on with one click to make sure that their buckets never allow public access today or allow public access in the future. And the impact has been remarkable. Millions of AWS customers have adopted S3 BPA. By meeting the users, customers, where they are, we've achieved widespread adoption across the base. 5 years later, after we launched S3 BPA, the impact has grown exponentially because we made it even simpler. S3 BPA is now turned on automatically for all new buckets that users create. We call this zero-click formal methods. Customers get the security and consistency benefits without them even having to click a button, click a checkbox, because when they create that new bucket, they get the whole power of it with it. It's formal verification by default while you're trying to scale out. There's another powerful dimension to this story. Not only is BPA the default for all new buckets, it's become foundational to how we build new services. S3 for Outposts, which is a different service, launched with BPA built in day one. We evolved from adding formal methods to after the fact to making them a core part of our service architecture from the very beginning. It's always on for S3 Express One Zone. It's always on for DynamoDB, a very popular database. And this is public documentation. We very proudly talk about how we use automated reasoning to achieve the goals that we want. But the truth is that the users don't actually need to know any of this, because we aren't trying to change their expertise or intuition. We just give them out of the box. This is what meeting them 100% of the way means. We are building a more solid foundation under that experience. So this was an example of how we did a one-click to a zero-click process for security. Now I'm going to talk about two other examples where we achieved very similar results. Okay. You're thinking, okay, that was one check. How do we continue to build on that foundation? How do we go beyond public? Do we even need to go beyond public? Looks like a great success story. Why do we need to go beyond? I want to go back to our discussion of the S3 APIs. There were about 100 APIs to S3, distinct APIs today. And there's a rich amount of detail what you can do with your S3 bucket. But block public access is a very coarse property. It just gives you Boolean, public or not public. And no offense to Booleans, they're great. Like we all love Booleans. The whole computing world is world on Booleans. But the customers and users wanted to have more fine-grained notions. They were telling us, don't tell me if my bucket is just public or not public. Tell me if it's correct. It's like, okay, we've gone back to the policy analysis. Does it mean we end up doing our SMT analysis again? Is it time to dust off and teach Venn diagrams to our customers? No. Remember, our goal is to do this without teaching them formal methods. We go back to that drawing board. How are the users solving this problem today? How do they actually, in their own heads, sort through the allows and denies and negations and the logic of policies with all of these expression matching algorithms? And if there is access to what we realized is the users mentally group up accesses, because a resource can have millions of access paths. And they're similar with slight variations. So the grouping that users create is based on either a particular account, a particular role, particular action, or what they were calling groups of finding. And we had to keep digging. Okay, what are the desired properties that these folks have? And this took a bit of back and forth. They did not give us this in these terms that I'm going to present, but this is how we came up with these notions. We have to be able to trust the findings. It's not just enough to say, hey, identify some of the accesses. We want them all. And in our parlance, it means they need the findings to be sound. If access is represented by some finding, then they should be able to verify the safety of access by verifying the safety of each finding. Okay? We needed the findings to be precise. We could get soundness with a single finding. Oh, everybody has access, right? The top of your lattice. But that's not useful. To be useful, we want findings to adhere closely to the actual access that is allowed by the policy. And finally, we want the findings to be compact. We could get away by soundness and precision by returning 1 million billion findings for accesses that are allowed on the resources. But no human could ever review them. So instead, we want the set of findings to be reasonably small. What does that look like? I'm going to walk through an example a bit more in detail. I said, if there's no policy attached, there's no access. Access is denied by default. So suppose you have an S3 bucket where you store your data and you're going to attach a resource policy to say only the right people have access to my data. So we'll add an allow statement to grant access. The one this grants access is to 2 virtual private clouds, or called VPCs in AWS parlance, where the request originates. So think of VPC as a network. And that says any requests from VPC A and VPC B are allowed access to my data. We will add another allow statement to grant additional access. This one grants access based on the organizational ID of the requester account. An organization in AWS is a group of accounts, and an organization ID is the unique identifier of an organization. This statement says everybody from organization O2 has access. And finally, we add a deny statement. This statement removes access that were granted by the allow statements. It uses a conjunction of conditions, one of which is negated. So let's look at carefully at what it's saying. If the request originates in VPC B and the requester is outside of organization O1, deny access. And here we can see the combined effects of all these policy statements. And I know I was making fun of Venn diagrams before, but don't worry, this is not what we show to our end users. Instead, we use stratified predicate abstraction to figure out what should the findings look like. And ideally, the findings should be in terms of the way access is controlled. Looking at this policy, we can see one of the ways that access control is done is through these source VPC condition. Let's extract a set of predicates for this variable. So we have ptop, which says the source VPC doesn't matter. We have PA and PB that restricts VPC A and VPC B. Similarly, access is controlled through the principal org ID, the organization ID we talked about. And when we extract predicates for this variable, we see qtop, Q1, which represents organization O1, and Q2, which represents organization O2. And the simplest way to generate findings for these is to conjunct them. With these predicates, there's 9 sensible cubes of conjunctions we can form. Here, they are laid out in a 3 by 3 grid. In the top left, we have the most general one, that everybody has access to everything. As we move right, we get more specific findings, such as organization O1 has access. And as we move down, we get even more specific findings that says organization O1 coming from VPCB has access. And these cubes are all the possible findings that we can turn them into. So what's left is to select a sound and precise subset of them. Okay, let's start. We can start with a single finding. Everybody has access. So the question we ask is, can this be made more precise while preserving soundness? Can we replace this finding with these 4 more specific findings? And the answer here is yes. Every access allowed by the policy and by the finding ptop, qtop is allowed by one of these more precise findings, which means we can remove the ptop and qtop finding. What about PA and qtop? Can this finding be replaced by more precise findings? The answer here is no. Imagine a request coming from VPCA and a third organization O3. This would be allowed by the policy and by the PA qtop finding, but not covered by either of these 2 highlighted findings. Thus, PA and qtop is essential. It will be one of the final findings we return. Moreover, the 2 more specific findings will not be returned. These findings are already covered by PA and qtop. And we continue this process. We iterate on this process, and in the end, come up with 3 findings at the end. Here they are written out. We have first, which says VPCA has access, the second that says organization O2 has access, and the third one that says VPCB with organization. So VPCB that is contained in organization O1 has access. So we've gone through our predicate abstraction and done all of that. So we went back to our original set of properties and formalized them. We showed to our users the desired properties, and I'm going to give a taste of the formalism here, but not going to define all the symbol. We formalized soundness in coverage, which says the set of accesses allowed by the policy is a subset of the accesses allowed by the findings. So it's an over-approximation. This is how we know it's sound. We formalize precision in called irreducibility, that every finding represents some access which is not covered by a more specific finding. This helps us reduce the number. And finally, we formalize compactness as a notion of minimality, which says removing any finding from the result shrinks the set of accesses allowed by the findings. It's also instructive to see how closely we achieve our informal properties of sound, precise, and compact. Here's our policy and actual access that is showed in green. And here's the findings shown as bolded white borders. The bold borders surround all the green areas, so our findings are sound. There's only 3 findings, so our findings are compact. What about precision? We are almost precise except for this one spot here. There's accesses that are not allowed by the policy but are covered by the findings. So to do that, we would need to introduce negation. And in practice, what we found is negation is really hard to reason about for the end users. So, and ends up being a frequent source of confusion and subtlety. Not A and not B with, that is negated to not C and A and B. It adds a lot of cognitive overload. And we cannot have soundness and precision complete to this thing based on the way users want it. So we decided to have an over-approximation, a reasonable one, and willing to sacrifice a little bit of precision for the sake of simplicity. The other great thing about findings is they are modular. Each finding can be understood on its own. So contrast that where the policy allow deny statements interact with each other. Here, the findings are modular. People can look at it and say, oh, I can see this one is okay, yes, it's acceptable. This one's, a security engineer can go and look at it and say, this one's not. I don't know about this one, and I will have to go to my development team to ask if it's not. And this is a bit more subtle, but the findings are more always sensible. What this means is, take this policy which is allowing access based on the principal org ID. It grants access if the org is like 01, 02, 03. The star says, or 07 star. The star says it can match to anything, which is syntactically legal but semantically nonsense. In traditional verification, nothing stops you from verifying the supposed correctness of the policy. Your specification can be as questionable, semantically questionable as your policy. But in our approach, we control the specification language. We only generate predicates for the things that make sense. There is no predicate for the dubious notion of 7/8 star. So when our algorithm asks, can this finding be refined into these more specific findings? The answer is no, because there are accesses that are coming from the 7/8, say 7/8/9 organization, which will be allowed by the policy and QTOP, but not by these more specific findings. So the finding the user gets is everybody has access. And again, this is part of that approximation that we've not restricted access to any one of the organizations in any meaningful way. So these findings are sensible by design, and they guide users in making sensible decisions about their access control. Here is what the Access Analyzer service looks like in the AWS console. This is the landing page for it. If you take a look at the workflow for users, they start their service, review findings, and take action. They're not learning a new way of thinking about access control. Instead, they take their existing way of thinking about access control and apply it on a much stronger foundation, a foundation that is built on automated reasoning. Here's the findings overview page that I've attached to one of my buckets. And the findings that it returns, it's exactly the policy that I worked through it, and they are cubes of our predicates in pretty printed form. It's a way how domain experts think about access on a stronger foundation. They can click into the details of the finding. Here's that predicate again. And it gives the user additional information, how the resource is shared, how long it's been shared. And if the user decides it's intentional, they can archive the finding so it doesn't show up. And if the user decides it's not intentional, then we guide them to the appropriate console to fix the finding. The impact of IAM Access Analyzer tells a powerful story. Today, we are analyzing hundreds of millions of resources every single day. All the customers are getting benefits of formal methods without ever even knowing what exists under the hood. We've expanded on these capabilities of Access Analyzer. It now has checks for unused access. It has helping users identify, remove unnecessary permissions, policy validation, and there is also a power user to say how to ensure securities follow best practices. All of these was made possible by now having domain-driven foundations for our access control. For the last part of this talk, we're going to switch gears and go into cloud governance. Show of hands, how many people know or heard of cloud governance? Great. The rest of you will find out in a few minutes. Remember back to these combinators that AWS provides. I made them sound so nice and neat, but today I'm going to tell you a secret. These functions have side effects. Lambda isn't just a combinator, it creates a resource. It's known as a Lambda function. SQSQ creates queues. S3 creates bucket. DynamoDB creates tables. And these are all resources that need to be configured correctly. The question that we had about access control, who should be configuring them, who should be configuring access control, and who should have access to what, comes back to the configurations of resources as well. You probably want to make sure that the resource configurations of such critical resources is done correct. Let's zoom into an example. Let's look at a DynamoDB table. The types of questions, example questions we'd want to ask about its configuration: is it encrypted? Is deletion protection enabled? Is it backed up? Is point-in-time recovery enabled? Is auto-scaling enabled? Is it well within throughput limits? And there's several hundreds of these resources, each with many different questions depending on the requirements. The requirements can be around security, availability, durability, cost savings, and these are the things that are referred to as governance criteria. So AWS Config is a service that customers use to gather their data about their cloud infrastructure and cloud configuration, the resource configuration, and ask questions. So today, we are going to talk about the rules that answer these questions. So config has these managed rules. There's about 630 of these today, and these are 630 programs that we want to prove correct. So how do we get started? We're going to zoom into one specific example here. So point-in-time recovery for a DynamoDB table, it's also called PITR. It's a database backup and recovery feature that allows you to restore a database to a specific moment in time. This is particularly useful when you need to recover data from a critical error or unwanted change. Here, we are looking at the JSON blob of a DynamoDB table metadata. And this blob provides information about table configuration. We want to ask, is PITR enabled for this table? There's a hint. It is. What about this table? Another hint. It's not. Okay, this is easy. We can write a simple Python program to answer this question. Let's try out. If we run this simple Python program on this table metadata from the first example, the Python program returns compliant. Okay, let's keep going. We run it on the other example. Not compliant. So good. So far, so good. Simple, right? What does it say on this table data meta configuration? And it's a bit hard to read JSON, so I'm going to say there is no PITR field defined in this blob like we did in some of the other examples. The Python program will say key error because it's not there. It's looking for something that's not there. The answer is it should be not compliant, because if it's not there, the field doesn't exist, it shouldn't be there. So here's the actual complete rule as a Python program. And you can refactor this in many ways, but this is the core logic. It has a lot of incidental complexity, obscures the real logic. And I presented a very simple example, but even for other rules, it can get very complex. But our question was, how do we build a foundation under this? We really, really struggled here because they're trying to write these rules in Python. And Python as a formalized foundation, that seemed hopeless. Python is too rich, too big. So we wanted to start looking deeper. How are the users actually using Python? And what we realized is, for the most part, they're using a very small portion of the language. Something you may even call a simple decision logic that contains libraries and API calls. So we decided to build the foundation here. We decided to build, for this decision logic, a domain-specific language which codified the restrictions and limitations of what they were doing. And our code name for this DSL is Weirwood, for any Game of Thrones fans, no? Yeah. In the audience. But what this allowed us to do was to remove Python from the story altogether. And we ended up with a much simpler system. But you're saying, wait, we were supposed to meet them, all the way. Are we breaking our own rules? The answer is not really, because Python is not their domain. They're not Python programs. They're security engineers. And a conversation that never happens between security engineer is, hey, what if there's a key error due to a missing field? Can we use triply nested if-then-else branches? No, that's not a conversation that's happening. But the conversation that is happening between the security engineers is, hey, can we check if point-in-time recovery is enabled and by default assume it isn't? So they are talking about their domain in terms of a decision logic. And what does this decision logic in Python look like? We end up with ad hoc type checking. We end up with evaluating properties and defining default behaviors. So we take that and turn it into our DSL. Here's what a rule looks like in Weirwood. It has strong typing, it's declarative, and it has sensible defaults. But is it correct? Okay. How do the domain experts today think about correctness? We keep going back to our definition of that. This is the program from before, but there is something I left out that security engineers already do today. They write a comment, a large human-written structured comment that outlines all the desired behaviors of the rule. And the domain experts also put comments on the return statement, trying to tie them to the scenario. So the scenarios are like specification, code is the code, and the comments on the return statements are like a proof, a traceability proof that the domain experts are trying to show themselves that the code matches the scenarios. How do we translate that to Weirwood? The specification is the same, the code is shorter, but now we're not even clear where the proof goes. In some ways, we made things harder by simplifying the code. Okay, can we just teach them how to write a formal spec instead of handwritten scenarios? No. Our job is not to teach or replace. So how would we build our formal foundation? They're structured, but they're handwritten, but not with always consistent wording style. So we thought about this problem a long time until we figured out we could invert the problem. What if we made the code the primary thing and the generated scenarios were just a consequence of the code? And these scenarios very much look like path conditions that you get from symbolic execution. I'm not going to go into that, but for those who don't know, like symbolic execution is an enumeration, a symbolic enumeration of all the logical statements in your rule. And these rules are small. So let's see what it does. What should a rule look like for this? What should the scenarios look like for a given rule such as this? One scenario is that logging is not enabled, so the result is not compliant. Another scenario is that logging is enabled and there is unlimited retention, so the result is compliant. Next, it says logging is enabled, there is no unlimited retention, but there's at least 90 days of retention, result is compliant. And finally, it could be that logging is enabled, there's no unlimited retention, and there's less than 90 days of retention, and the result is not compliant. And this is the rule that says the resource must be logging enabled, and it must either have unlimited retention or at least 90 days of retention. That's what the rule is checking, and the generated scenarios cover it. Previously, humans had to manually write those scenarios. So what makes the scenarios great is they're automatic, they're generated automatic, they're simple, each scenario is just a conjunction of the simple conditions. They're independent, each scenario can be considered in isolation, and we can write tests on it, and it is exhaustive. Each behavior is covered by a scenario. So what do we use it for? We use it for validation, that to understand the behavior of the rule. We use it for testing that requires 100% scenario coverage. We use it for traceability. Every time a rule executes, it gives you a result plus a scenario number, and it gives you documentation. Non-experts can now easily read what the rule's behavior is. So the role of the theory in Weirwood is that there's a core theorem. Given a Weirwood program, you can concretely execute it or do scenario generation, and there exists a scenario where all conditions are satisfied and it predicts the actual execution result. This is the theory that ties everything together. This means it is deterministic. There's no errors pointing off in random, made-up directions. It's correct every time. It's deterministic. And this is exactly what we've been doing. We've been generating these scenarios. We're building a formal foundation underneath and not replacing or trying to teach. There's one final thing I want to talk about, what cool this thing does, is a rule's behavior can actually change over time, even if nobody changes the rule. How is that possible? So here's a rule that checks if the encryption is post-quantum. And here's the enumerated types of the encryptions. But what happens when a new non-post-quantum encryption type is added? Drift. But in this case, the way the rule is written, we are fine. The rule is not wrong. But what happens when a new post-quantum encryption type is added? Drift. The case is unsafe. Notice, no matter how we write this rule, we will end up with unsafe drift in one direction or the other. So the way we leverage scenarios to help solve this problem is, notice that these scenarios are a little weak. The idea we use is to use type information to enhance these scenarios. Okay, that's better. Now the type information is actually in the rules itself. Then we have stronger scenarios, which are more descriptive. And now, watch what the drift does to the scenarios. Add a non-post-quantum algorithm cha-cha, drift is detected, and the change is in the scenarios. Scenarios tell you exactly what the new behavior is. You can verify that it's safe. When you add a non-post-quantum cha-cha algorithm, drift is detected, and you can keep going on. When you add the post-quantum algorithm Sphinx, drift detected and fixed. So now you have a way of continuously checking whether your rules stay consistent, because underneath the environment, it's evolving, it's processing everything. So not only is it proving the correctness of rules point in time, it's proving the correctness of rules as it goes continuously. So once we've had the foundation of automated scenario generation in place, our problem of drifted away. And this is what building upward means together. We are amplifying the expertise of the domains rather than replacing it. And we now have a structure we build together on top rather than, again, saying, no, you're doing it wrong. So what's next? I talked about how we are scaling out for these critical areas of security, identity, and governance. But not just each of these areas. We were building on top. We took S3 block public access and how we continued to build on it, turn it on by default, turn it on for new resources. For IAM Access Analyzer, how it enabled one-click customizability for your access management. For cloud governance, we did drift detection, and things I didn't talk about in this is we are doing the same with proactive controls and preventative controls. So if you want to learn more about all the applications I've talked about, there's an automated reasoning section on the Amazon Science website. It has links to our research publications, blog posts, and there's actually even YouTube videos about how we talk about this work to our customers. And last but not least, please make sure to come tomorrow at 2:45. Mariana's going to talk about how we've been scaling up, because we replaced the authorization engine that runs every single request to AWS, which is trillions per day, with the verified version without anyone knowing that it happened. So that is super cool. And thank you again for your time. I'm happy to take questions.
Thank you so much for your presentation. Maybe we have time for one question. We don't really have time, but maybe one question, if there are any, or... yeah, one question, and then more discussion.
Yeah, I'm happy around, so I can take more.
Yeah.
Hi there. Thank you. It was a great presentation. I'll just ask one question. I want to spare you, delay anyone from getting coffee. So, how far up the software stack do you think this approach can go? Right? This idea of bringing formal methods capabilities, right, to developers. But of course, as we get further up, we're going into okay, well, is there business logic sound further up, right? And there are questions about to what extent you need the developer's involvement in that, that formal verification, right? So I just wanted to get your thoughts.
So I think the problem is, at least in our opinion, like when you're trying to solve the correctness of a business logic problem, we often get mired into, hey, they're representing their business logic in Ruby or Python or Java, and we get mired by the generalizability of the current tools they have.
Right.
And I think if we start saying, how do we just give them the right tools? The example that I presented in the last thing, the engineers are writing it in Python not because they love Python or think the right tool for this is Python. That was the best they had. And we believe it's true for hundreds and thousands of business applications as well, where a lot of folks are doing things in tools and systems because it's not specific to them. One of the things I believe as the AI boom picks up, and if it fulfills its promise, that doing domain-specific programming will get easier and cheaper, more cost-effective, as well as with the tools.
Great, thank you.
Thank you again. And this is a present from the local organizers.
Okay.
Thank you for agreeing to
Thank you.
So Neha is available
I'm
for
happy to
more
chat,
discussions, and now we have time for a coffee break. So thank you.
Thank you.